In this video, we're going to go over topic 5, section 7, day 1, which is exponential functions. For the most part, we will be using logarithms to solve and create equations that involve logarithms, but we're given exponential equations in this entire lesson. So an exponential equation is an equation that contains variables in the exponent. So the thing that I'm solving for is in the exponent of the equation, not as a base or a constant, or not constant, but term. So then the property of equality for exponential equations states that as long as we have a positive b and b not equal to 0, then b raised to the x power equals b raised to the y power if and only if x equals y. So that means that since the bases are the same, in order for those two statements to be equivalent, then the exponents have to be the same as well. And if and only if means that I can be given two equal quantities, and I could raise them as a power, exponentiate them with the same base, and that would still be a true statement. And then, so in words, this says that if two powers of the same base are equal, then their exponents are equal. So that's the property that we're going to use in this first example. The converse of that is that if I have two exponents that I know are equal, then the powers of the same base are equal. So that means that the whole equation is equal. So for these first problems, we are solving an exponential equation using a common base. So what this means is that we want to make a common base. So right now we don't have common bases in any of these equations. However, we do have numbers that can be written as a base of the same, as a power of the same base. So if I think about 1/2 is actually a power of 2, as is 4. So 4 is a little bit easier. We can think about 4 as 2 squared. So if I change that 4 that's being raised to the 3x power to 2 squared, I can think about that as 2 squared to the 3x power. I want to do the same thing with the 1/2. Remember that a whole number turned to a fraction means that I had a negative exponent. So 1/2 is actually 2 to the -1 power. And so now I've rewritten these expressions so that the base number is the same. I do have to do a little bit of simplifying before I can apply the property of equality. So what that means is that I want to use the power of a power rule. So remember that when I have two exponents next to each other with parentheses, I multiply my exponents. So I'm using, remember the properties of exponents are that mad spam. Whoops. So when I'm multiplying my bases, I add my exponents. When I'm dividing two bases, I subtract my exponents. When I have parentheses, I multiply my exponents. So this is going to be 2 to the -1 times x plus 7 power is equal to 2 to the 2 times 3x power, which means I really have 2 to the -x minus 7 equals 2 to the 6x power. And so now I have what I was looking for. I have two bases that are the same, right? I have a 2 here. And so what I can do then is ignore the 2 and notice that this was x and this was y. And so that means that x equals y. So that means that I can take -x minus 7 and set that equal to 6x. So once I have the same base, I can then ignore the bases, and then I want to solve for x. So since I have -x and a 7 over here, I want to leave the 7, so let's add x to both sides. And so that gives us that -7 is equal to 7x. And then finally, dividing by 7 gives us that x equals -1. Since exponential functions have a domain of all real numbers, we don't have to check our solutions for these problems. So we can leave, we can just leave that as the answer. We don't have to check it. So then we're going to follow that same process for each of these other two examples. And so remember that our first step is we're trying to rewrite so that they have the same base. So let's just restructure with the parentheses like we did for the first one. So I'm going to leave a space for what I'm going to change 25 to. That's raised to the 3x power equals, I'm going to change 125 to something. That's raised to the x plus 2 power. And so I want to rewrite 25 and 125 as the power of the same number. So 25 is 5 squared and 125 is 5 to the 3rd power. So we're going to rewrite them that way. So 5 squared to the 3x power is equal to 5 cubed to the x plus 2 power. And again, the process is going to mimic exactly what we did here. So we have to use the power of a power property to rewrite this as 5 to the 2 times 3x power is equal to 5 times the, 5 to the 3 times x plus 2 power. So what that means is that we really have 5 to the 6x is equal to 5 to the 3x plus 6 power. And so now that we have those matching 5s as our bases, we can just write the exponents. So 6x must equal 3x plus 6. Which means that since 6 is the only constant, we want to subtract 3x from both sides. And that will give us 3x equals 6. So then dividing both sides by 3 gives us that x must be 2. And again, exponential functions have a domain of all real numbers, so it's not necessary to check your answer. You could always check your answer just to make sure that it equates to the same value. And then for the last one, we've got 0.001 equals 10 to the 6x power. So for this one thing to note is that 10 is not a power of something else. So I can only think about 10 as 10 to the 1st power. That tells me that I must be able to think of 0.001 as 10 to some other power. So think about a decimal works the same way as a fraction. And so how our first problem, we had that 1/2, that 1/2 became 2 to the 1. 10 to the -1 would be 0.1. And so then if I have 0.001, I need to move that 2 more spaces. So that means that I would have 10 to the -3 power, right? So if I think about this, this is 1 over 1,000 is what 1,000th is equal to, right? So 0.001, that means that I have 0.1 would be 1 over 10, 0.01 would be 1 over 100. This is 1 over 1,000. Since 1,000 is 10 to the 3rd, I can equivalent that to 10 to the -3rd power. This one simplifying is a little bit easier because I don't have anything to multiply the first one by, and this one I'm just multiplying it times 1. So this is really just 10 to the 6x. So then when I am equating my exponents, I have -3 equals 6x, and then dividing both sides by 6 will give us the answer, which is going to be -1/2. So x is equal to -1/2. Okay, so this example, we were able to rewrite the exponential equation so that both sides of the equation had a common base. And by doing so, we're allowed to then ignore the base and just set equal the exponents and solve like that. In example 2, we're asked to rewrite an exponential equation as a logarithmic equation. So a logarithmic equation contains one or more logarithms of variable expressions, meaning the variables inside the logarithm, the same way that the variable was in the exponent in an exponential equation. So the property of equality for log equations is very similar to the one for exponential. So if I have log of the same base of two values set equal to each other, then those values must be equal. So again, I can ignore the log base b if they're equivalent. So in words, I underline just the part that we're going to be using in this lesson. We will use it in the other direction tomorrow in the next day 2 video. If two logarithms of the same base are equal, then the quantities are equal. And what we're going to look at is we have two quantities that are equal, and then we're going to create logarithms that are equal. So what's going to go on is that we want to be able to rewrite this so that we can just have logarithms. So to do that, we're going to use the idea I didn't change colors. Give me a sec. So we're going to use the idea that if I use a power of 10 to the log of something on both sides, so that we now have the same base, on both sides. So I see that I have 17. 17 is a prime number. I cannot make that as a power of 2, right? Because 4 is 2 squared. And so I'm stuck with this, and I cannot change it the way that we did in the previous example. So what I'm going to do is I'm going to use this idea that if I take 10 to the log of base 10, so I'm looking at a common log of both sides, so think about it as though I was exponentiating it like we did when we were solving equations back in one of the previous lessons. So I'm taking and doing 10 to the log power of both sides. And that gives me something where now both sides of the equation share that base 10. So what that means is that I can use the property of equality for exponentials that we used here, right? We made these have the same base, so we set the exponents equal. So these exponents just happen to have logs in them, but this tells us that this is equivalent to log of 17 equal to log of 4x. Okay, so this example is just asking us to rewrite the equation as a log equation, and this is the process that you will use each time. So you will always do 10 to the log of power if you're just asked to rewrite it as an equation of logs. So then for the next one, we're going to take 5x and 12 and replace the empty space with that in our process. So we're going to do 10 to the log of 5 to the x, excuse me, equals 10 to the log of 12. So they now both have a base of 10. So we can ignore those 10s, and that means that our new equation that's equivalent is log, sorry, got a mess going on over here. Our equation that is equivalent is log of 5 to the x power is equal to log of 12. Okay, so this example again is just practicing with changing it into a logarithmic equation. For our last example in this lesson, we are going to be solving exponential equations using logarithms. So for these problems, we have exponents on both sides of the equation. So we cannot just switch to log form if that was our preferred method for, say, a problem that looks like example 2, right? With problems like example 2, we could have rewritten this as log base 4 of 17 equals x, and then use the change of base formula to calculate. For these problems, the issue is that I have a base of 3 on the left and a base of 5 on the right, or 2 and 7, if we look at part B. And so what I have to do then is I have to just take the log of both sides. So I'm going to use the property of equality for log equations and just use the common log and take the common log of both sides. Okay, so the first thing I'm going to do is take common log of both sides. So I'm going to take log of that 3x plus 1 is equal to log of that 5x. Sorry, 3 to the x plus 1. 5 to the x. I said that wrong. Okay, so our goal here is to get x by itself. Currently, x is stuck in a power. And so what we're going to do is actually use the power property of logarithms. And remember that the power property tells us that I can take an exponent and move it to the front. So that means that I'm going to move x plus 1 to the front of log of 3. And I'm going to take the x and move that to the front of the log of 5. So again, I'm taking the exponent and moving it to the front. I'm taking the exponent and moving it to the front by applying that power property. Okay, so I need to get x's on both sides. Currently, I have an x on the right, and then this kind of x plus 1 happening on the left. So what I have to do is I actually have to do the distributive property. So that I can get the x away from the 1. So what that means is that I have x times log of 3 plus 1 times log of 3. And that's equal to x times log of 5. So I want to be able to get each of the terms with x on the same side. So at this point, I'm ready to solve for x using inverse operations. So I want to move this term that has an x with the other term that has an x. So I'm going to subtract x times log of 3. So that I end up with just log of 3 on the left. And this part's where it gets a little bit complicated because think about this as a number. So log of 5 is just some irrational number. Log of 3 is some irrational number. I cannot do that subtraction and say that this is like x times log of 2. I cannot subtract those numbers inside the log because the log changes them. So what it really is I have to rewrite it as x times log of 5 minus log of 3. So I don't know what those numbers are just yet, but I know that they are some sort of number. So once I know them, I will subtract them. So then to get x by itself, since it's being multiplied times this subtraction, I'm going to divide both sides by log of 5 minus log of 3. So that means that we are going to take a calculator and calculate log of 3 divided by log of 5 minus log of 3 to estimate this value. Okay, so if we look at Desmos, and again, I have that scientific calculator up, we're going to type that in. So we have log of 3 divided by, I'm going to put, so then log of, and I'm just going to type the number. I don't know why I've been doing that. Log of 5 minus log of 3. Remember that you can use your keyboard to do these values. They did not give me a number to round to, so I'm just going to do to the nearest hundredth for this. So I'm going to do 2.15 as the answer. So the answer is about 2.15. Okay, so I have an exact value of log of 3 over log of 5 minus log of 3, and that approximates to 2.15. So I know that these look messy, but the procedure is the same every time. So you'll see as we do this next one, we're going to go through those same steps. So I'll color code with the same colors to kind of help you visualize that. So our first step is to take the common log of both sides because we cannot rewrite them to have the same base. So we're going to take the log of 2 to the 3x is equal to the log of 7 to the x plus 1. And so then from there, we're going to use the power property. So we're going to bring the exponents to the front. So we're going to have 3x times log of 2 is equal to, we're going to bring x plus 1 to the front times log of 7. So then remember that we want to distribute any expressions that have multiple terms. So for this first one, 3x times log of 2 is just that. There's no value that I have to distribute. I don't have a sum. Technically, you might want to think about this as 3 times x times log of 2. So x is being multiplied by 2 things at this point. That will come into play when we're doing our division. And so that's equal to, we're going to distribute x plus log 7 into x plus 1. So we're going to do x times log of 7 plus log of 7. So from there, we have 2 logs on one side. One of them has an x, the other one doesn't. On the left side, we have a log multiplied by an x. So we want to move the log with the x over with the other one. So I'm going to subtract x log of 7 from both sides. And so that's going to give us, remember that we take the x out and we're thinking about these guys as coefficients. So I have x times, and when I write this, I'm really just kind of ignoring the x. So I took the x out. So I'm going to write whatever is left that I didn't highlight together. So that means that I have 3 log of 2 minus log of 7. Okay, so when I'm writing that in that nature, and then on the right side, I just have log of 7. Okay, so when I combine like terms here, my like term was the fact that they had the variable x. So I took that variable x and wrote it. Remember, normally if this was like the number 5x minus 2x, I would just subtract 5 minus 2. So that's what this part in the parentheses is representing. I'm subtracting whatever's left from the x the same way that I would do it in a numeric problem. So then, since I want that x by itself, I'm going to take and divide both sides by what it's being multiplied by, which is 3 log of 2 minus log of 7. So for x, that gives us the equation x equals log of 7 divided by 3 log of 2 minus log of 7. So then if we calculate that to get our approximation, we're doing, I thought I can just type log, I don't know why it's doing that. Log of 7 divided by log of, 3 log of 2 minus log of 7. And so that gives us 14.572. We rounded to nearest hundredth in the previous one. So let's do that same thing there. So the 7 is going to stay a 7. So that gives us an estimated value of 14.57. Okay, so x is log of 7 divided by 3 log of 2 minus log of 7, which approximates to 14.57.